Hello, my name is Wade. As I pointed out in part 1 of this video series, I recently developed an Excel spreadsheet that allows the user to model what a 100% renewable energy supply would look like for countries such as the USA and Germany. Why did I choose those countries? It's because those are the countries I could get data for. It's not so convenient getting data for other countries, apart from Australia. I've also got an Australian model, but it works a bit differently than the ones I have for USA and Germany. So in part 1 I described how to use the inputs for the wind and solar generation, how to vary them, and for slow and fast charging storage to supply 100% renewable energy to a grid to meet demand. If you have not watched part 1, you should do so, otherwise some of this might not make much sense. In part 2 I'll explain how we can add extra demand to the grid, because the current grid, the coal and gas-fired power stations on the current grid, aren't the only forms of polluting fossil fuel energy. There are many other uses of fossil fuels which are as equally or more polluting as the coal and gas-fired electricity generators. So one of those forms is road transport. Of course they use gasoline for the Americans, or I don't know what the Germans call petrol or gasoline, but they use it for most vehicles on the road. They're very slowly, there's an introduction of electric vehicles. So what we want to model is, if we replace all of the fossil fuel vehicles with electric vehicles, how will that affect the grid? How much more power will we need? Where will that come from? How much will it increase demand? So here currently demand is 4.14 million gigawatt hours for the year, and we can see that I have this on the wrong setting, sorry. Okay, if we change it here, working with the 2021 year, so the demand here was currently, I'll put it up on the screen. So currently demands at approximately 4 million gigawatt hours for the year for 2021, that's electricity demand. If we electrify 100% of the road vehicles, convert them to electric vehicles from current fossil, or replace the current fossil fuel vehicles with electric vehicles, what will that look like for demand? So here's the current value, 4 million. With 100% of road transport electrified, that will turn to, and to do this you change the 0 in cell CB13 to anything other than 0. I'm going to type a 1 in here, and we can see that the demand down here changes to 4.67 million, so an increase of about 16.7%. So that's all the electricity that would be needed to about 16.7% more demand to electrify 100% of road transport. That's an estimate, of course. We won't know the real value until we get it. I'll explain how I came up with that value in a moment. Now, how did that affect the grid? We saw there's only a very small increase in other generation, because most of that extra power, so other generation, went from 2.65% up to, of the demand, up to I believe it was 85%, yes. Why did other generation increase by so little compared to we now require next to 16 to 17% from the grid? We haven't increased the amount of wind or PV capacity. The reason why is because there was already a surplus of wind and PV power. The curtailed wind and curtailed solar energy power, or energy that hadn't been used, that was curtailed. So that surplus energy can be used to recharge the batteries in the electric vehicles. So you wouldn't need, on a 100% renewable grid, chances are you wouldn't need to add a lot of extra generation to supply the electricity needed to run all those electric vehicles. you would already have that generation. It's just that some of it would have been surplus to the current demand, the demand without the electric vehicles. Okay, so very quickly I'm going to go through where I got the data from for the electric vehicles, where the extra demand comes from. I'm saying that the electric vehicles will require, on average, for passenger and light commercial vehicles, so cars, pickup trucks, SUVs, motorbikes, on average, they're going to require, in sum, about 48 gigawatt hours of energy per hour. So you multiply that 48 by 24 to get the total amount of energy per day. That's based on data from the US Department of Energy showing that 70% of energy use for road vehicles in America is passenger and light commercial vehicles, while the other 30% are trucks and buses, larger vehicles. Now for trucks and buses, the other 30%, they use on average 20 gigawatt hours of energy per hour. They would be using that. How I calculated those, apart from using the US Department of Energy figures, I said that the number of vehicles of all types will be 75% of whatever the population is. So the US, I think it was 2022 census, the population was 335 million. Might be in 2020, I'm not sure of the year. So I said the number of vehicles will be 75% of that. And where I got the energy use for all those vehicles is I couldn't find data for the US or Germany directly, but the US and Germany have very similar road transport use patterns as Australia. And I did have the Australian data. I'm Australian myself, so I already had the data for that. And so I just substituted the Australian data for the US data. The Australian data comes from the Australian Bureau of Statistics. This is a 2020 study into road transport use in Australia. And the data of interest here is it showed how far, also had the number of vehicles, percentage of each type of vehicle. They split them up into vehicle types, which was very convenient and necessary. And it showed how much each of those vehicles travelled per vehicle each year on average. So a passenger vehicle, cars and SUVs, travelled on average 11.1 thousand kilometres per vehicle per year. Motorcycles 1.9 thousand, light commercial vehicles, so I think pickup trucks, 15.3 thousand kilometres per vehicle per year. Rigid trucks, so furniture trucks, 21.1 thousand kilometres. Articulated trucks, that'd be semi-trailers, 78.3 thousand kilometres per vehicle per year. And non-freight carrying trucks, 13.7 thousand. And buses, 24.6 thousand kilometres per vehicle per year. So once I had that data, I was able to put it in a spreadsheet. And I made an estimate based on my research in this field of, for electrical vehicles of those types, what would be the average energy used per kilometre for each of the type of vehicles. These are estimates. You won't know exactly what it is until it happens. So for passenger vehicles, they range from small sedans up to large SUVs. I'm saying the average of those would be about 180 watt hours per kilometre. That's probably realistic. That's the best estimate I could give. Small passenger vehicles use as little as 110 watt hour per kilometre, small sedans. Large SUVs can use over 200 watt hours per kilometre on average. So I'm just saying 180, it might be less, it might be more in reality. We won't know until it happens. Motorcycles 50 watt hours per kilometre, light commercial, again pickup trucks 220 watt hours per kilometre. That might be a slight underestimate, it depends on the size of the light commercial vehicles. Rigid trucks, again furniture van type size or furniture truck size, 500 watt hours per kilometre. Semi-trailers, articulated trucks 900 watt hours per kilometre, non-freight carrying trucks 400, and buses 500 watt hours per kilometre. So that's the watt hours per kilometre multiplied by the kilometres per year that each vehicle has travelled, multiplied by the number of vehicles, and so on, to get the total energy use of each type of vehicle per year. Took weighted averages and got values for the US of 48.18 gigawatts or gigawatt hours per hour for the passenger and light commercial vehicles, and the 20.55 for the trucks. So that's where the data comes from. Let's head back to the spreadsheet. So that's the energy used by the vehicles on average. Where they appear in the spreadsheet is for the passenger and light commercial vehicles. That's the power in this coming out of their batteries, out of the EV battery. And for the trucks and buses, because the trucks and buses are used for work, they have to be recharged at every opportunity. So I put them as a constant draw on demand by adding it to the demand. The current demand, which was in this column, I just added that 20 whatever gigawatts divided by the efficiency of 0.92 into directly to the demand. So it's can't be met by flexible supply, it just has to be met. It's part of the normal demand now for the trucks and buses. For the passenger and light commercial vehicles, I'm including them in this as a third type of storage. So they're going to be charged when there's excess wind and solar, and they're going to be discharged when they can be discharged, of course, the vehicles constantly, but they can also be used for vehicle to grid. So electrical vehicles can be used to supply power to the grid, and that's being modelled in this column here. Now, we want to know how many vehicles are being, first of all, what is the battery capacity of those vehicles? How can they be used as storage? Here I've got 20,000 gigawatt hours. That's a calculation. You do not put a value in there. That's a yellow cell. You only put values into orange cells. Where I got that 20,000 from is, I said, the number of vehicles is at 75% of the population, and then I multiplied that by an average battery size of 80 kilowatt hours per vehicle. That's probably going to be a slight underestimate, but it's what I started with. That calculation is done over in this cell here. 80 kilowatt hours per vehicle times 0.75% of the population is the total battery capacity of all those electric vehicles. The total charging capacity is calculated in this cell here. I'm saying that at any time 50% of the charging capacity of those vehicles will be plugged into the grid available for charging. 50% of the vehicles will be plugged in available for charging. And why 50%? Because I think chargers will become ubiquitous. So whenever you are not driving your car, whenever it's parked somewhere, there is likely to be a charger nearby that you could use if you wanted to do so. So chargers will become ubiquitous. They'll be in houses, of course, in garages, at the front of houses, wherever people park cars, shopping centre, business, government office, car parks, schools and universities, wherever people park their cars during the day, multi-storey car parks in the CBD. Like I said, wherever people park cars, there will be chargers, so people will be able to plug them in and charge whenever they are not driving. So I'm going to say that 50% of the vehicles are always available for charging. Of course, they're going to be swapping in and out as some will be parked, others will restart and will be replaced by new vehicles stopping and parking. Okay, and out of those 50% that are plugged in for charging, I'm going to say 50% are available for vehicle to grid. That is, that they are available to send power back to the grid. I'm going to have more on how those calculations are done in the next video when I go through the details of the calculations within the spreadsheet. Again, these are numbers, these are orange cells, so you can change these numbers and it will change the calculations in the spreadsheet. You can, if you think fewer vehicles will be plugged in for charging on average, less than 50%, you might think 30%, change it to a 0.3. If you think fewer of those plugged in vehicles will be available for vehicle to grid, or available for sending power back to the grid, you can change that value. I think it's more, change it to something larger than 0.5, any number between 0 and 1. Okay, so that's how the electric vehicles are accounted for in the grid. The other demand that we need to add to the grid, the other fossil fuel use that needs to be replaced by electrification is natural gas use in things other than power generators. Natural gas used in the power stations has already been replaced because it's part of demand, it's been replaced by this wind and PV capacity. So we're looking for the other uses of natural gas. Where we find information on that for the US, again, it's the US Energy Information Administration website, this page on natural gas. They have non-electrical uses of natural gas. Some of them are small and are actually used in the fossil fuel industry, so if the fossil fuel industry is much smaller, those uses will more or less disappear. The values we're interested in are the residential, commercial and industrial. Vehicle fuel is very small. That'll probably disappear as well. So residential, commercial and industrial, they have monthly data, so you can just download it. There's a way to download it, I can't remember what it is, but you can download it by month. And for Germany, I don't have that website up here, but I found a website where it's got the gas used by Germany, monthly data on the gas imports and also the domestic gas production in Germany for each month. So I downloaded the data for both of those, put it into spreadsheets. I'll show you what it looked like. For the US, this is the usage of gas. I've converted it to an energy equivalent in gigawatt hours. The data is in millions of cubic feet, so volume of gas that is used. The energy equivalence of that, just use the conversion factor of 0.29166 gigawatt hours per 1 million cubic feet of natural gas when it's burned. Okay, so how it's used is residential is in the blue. So this is in houses. In the summer, we can see that there is very little residential use, so these are the summer months. The blue is only small, so that'd be for gas cooking and maybe gas hot water heating. But in winter, we can see there's a much more gas being used in residences, and that would all be for space heating. That is heating the buildings, heating the interiors of the buildings people are living in, the apartment blocks, the houses. So that gas use has to be replaced. Commercial, so this is in restaurants, offices, small businesses, that sort of thing. They show exactly the same sort of pattern. Small use in summer. Again, maybe restaurants using it for cooking, gas-fired stoves and ovens, and hot water systems for, and so on, but mostly for space heating in winter. We can see big increases in winter when there's space heating. Okay, but not as big a larger increase as we saw with the residential because people go home at night from work. So they obviously turn off some of their gas heaters overnight, probably. And maybe that's the reason why we don't see as large increase as we saw with residences. Okay, the yellow is the industrial use, which is the main use by and large, the majority of use in the summer months, but it's the minority, just a bit less than half of the use over the winter months. But it's fairly constant throughout the year because it's been used to run heavy industries, say gas furnaces, high temperature gas furnaces in large smelters, for instance. They can use a lot of energy. So things like that. So that also needs to be electrified. So we can replace the gas use, but some of it can also be replaced by indirectly through the production of using electricity produced synthetic gases such as hydrogen using electrolyzers. So we need to replace all of that. For Germany, it's a similar pattern. This is the German data, so this is the 3 years. The Russian invasion of Ukraine caused a big disruption, a big fall in the imports. So it's hard to know exactly what I should have been modeling. I just took an average. So this graph here is to scale with this, which said this is basically the average for those months. Again, a higher use in winter, lower use in summer. In summer here. And I used that for all 3 years. I used the same data for all 3 years for Germany. For the US, I used the individual monthly values for the different years, the 2021 data for 2021, and so on, 2022 data for 2022, and 2023 data for 2023. Okay, so back to the spreadsheet. Where is it? Here it is. So, to include this in the supply is similar to the road transport. You go to the cell here where it currently has 0, that means we're not including electrification of those gas supplies, and you set it to anything other than 0. I'm going to set it to 1 and we'll see what happens to demand. So demand currently is the 4.67 million gigawatt hours once we've included the road transport, and we're going to see how it changes. So I'll set it to 1. We can see that demand has increased by about 50% up to 6.8 million gigawatt hours. A lot of gas is being used in the US, and Germany has a similar sort of figures, a similar sort of percentage increase. So, when electrifying the commercial and residential, the blue and green sections of the graph, I'm saying most of that is being used for space heating. We can see the vast majority of it was in winter when the people are using it for heating. So I'm saying if we substitute that gas use, we substitute heat pumps, electric heat pumps, which are significantly more efficient than the gas heaters, the gas furnaces for central heating and so on, we can save a lot of energy. We're going to save 60% of energy because the heat pumps are so much more efficient. Studies on this show around 30 that the electric heat pumps only use 30% as much energy as the gas heating, but I've put in a higher number because we're also replacing the gas cooking and gas hot water heating, which might be more efficient, where the efficiency gains aren't quite as large. So I'm saying 40%. So we're going to use only 40% of the electrical energy to replace all of that gas energy. You can change that based on your own research, but I came up with 40%. So anything between 0 and 1 there. For the industrial use, I'm saying we're going to replace, 10% of it will no longer be needed because it's being used in the gas industry. And since the gas industry is going to be closing down, I'm sorry for all the workers there. We're going to be, that 10% will no longer be needed. The other 90%, 70% of that will be replaced by direct electrification, say using electric furnaces instead of gas-fired furnaces in heavy industries, and other similar replacements. But 30% is going to be replaced using synthetic gases. So those synthetic gases have to be made by using electrical power, so they're going to use electricity. So we need to calculate an amount of electricity to run the devices that are going to produce that synthetic gas. So I'm just saying hydrogen electrolyzers. So just say we're going to replace all of it with hydrogen. It could be other things as well. So I'm saying we're going to need 400 gigawatts of hydrolyzers. Sorry, not hydrolyzers, electrolyzers to produce that hydrogen. And we're also going to supply some power from hydro. Now this 400 gigawatts of electrolyzers are only going to work when there's excess wind and solar. So this is flexible demand. The demand will only be there when there is surplus supply from wind and solar to run the electrolyzers. So it's an optional one. So now, once we've activated the gas and the electrolyzers, we have something down here saying, is there more supply than demand? We need that to say yes, and we need this number in this cell to be less than 0. So we need more supply. I'm going to increase the wind supply to provide that extra energy. So I doubled the wind supply, or more than doubled it. So now it says yes, and we have a large negative number here, negative 261,000. So now we're producing excess hydrogen. When it said no, the grid, for the electricity grid, supply was still meeting demand for most use, but it wasn't producing enough of the hydrogen gas to replace the 30% of the natural gas that we're replacing with hydrogen. So these two cells here are just saying, yes, we are now producing enough hydrogen to replace all of that natural gas that we're currently using, but which is polluting, which is producing CO2 and other pollutants when burned. Okay, so so that's how you introduce the natural gas into the spreadsheet. In the next video, I'll explain where the calculations are occurring for that natural gas. We have to show that this build works for all 3 years, so 2022, we have to show it works for that year as well. And I have the same build in here. No, I don't, because I just changed it at the start accidentally. So let's put it in here. So this uses different data. This uses the data for 2022 in the columns over on the left hand side, the data that I got from the US Energy Information Administration and from the German operated Fraunhofer Institute that gave data about the grid. So now I've replaced all these and it says yes, we are producing enough electricity to substitute for all of the electricity demand and also to produce enough hydrogen to replace that missing gas demand. This big negative number here. So now we go to 2023, so we see the same build, 2,300 gigawatts of wind, 650 gigawatts of solar, 300 of each type of storage. We have road transport electrified, we have gas electrified, but it says no, supply is not meeting demand. We are 407 gigawatt hours short. Now we could add more supply, but since that number is so small, 407, and this is, remember, this is the hydrogen gas that's being used to replace the natural gas supply, we created a lot of excess hydrogen in these previous years, which has been stored more than we need. So we can, so if there's a small amount here, a small positive number here, you look back and say, well, can we meet that demand from these larger negative numbers that we had in previous years? And if so, then you don't really need more supply. Okay, so that, and again, there's graphs. This is the outputs of all this is displayed in the tables, the relative percentages, how much energy is being supplied by each type of supply, and so on. The graphs are showing again supply in the bottom graph when the other supply is needed quite a bit. This is the 2021 year. This was the toughest year, by the way. The 2022 and 2023 had very little other generation. The wind and solar and nuclear was just about sufficient to meet all of demand on its own, with only a tiny amount of other generation. Okay, the graph up here shows charging and discharging of the storage types and demand. So the green line was the charging and discharging of the EV batteries. The blue line of the other types of storage, the pumped hydro and the stationary batteries. And I'll go through what these other, this grey line is the flexible demand, the electrolyzers for producing the hydrogen gas. The green line is the other generation, and the pink line is the discharge from storage when the storage types are providing power to the grid to help meet demand, and the red line is the demand, and the light blue line right down here is the hydro supply. Okay, so that ends this video. In the next video, in the last video, I'm going to go through the formulas on the left-hand side of the spreadsheet, which are all the calculations on how the spreadsheet actually works and produces these outputs from the respective inputs. So I'll speak to you again then.